let's investigate the properties of some interesting groups. First, let's begin with the circle group. I'm going to define the circle group in the following way, using complex numbers. So my notation for the circle group is going to be capital S with a superscript 1. This notation comes from the notation for n-dimensional spheres. So the circle is a one-dimensional sphere. And you can extend that concept up into higher dimensions. You can have spheres in 2, 3, or even higher dimensions. Another common notation for this is a capital T. That's the one-dimensional equivalent of a torus. So you can use the circle to construct the torus, the two-dimensional torus, and a three-dimensional torus, and so on. So that is covered in the topic of topology. But what we're going to focus on is the group properties. We're interested in the properties of the circle group. And I'm going to define this as the set of all complex numbers z. So z is an element of the complex numbers. Here I'm using the fancy C to denote the complex numbers, such that the magnitude of this complex number z is equal to 1. And I'll close this curly bracket. So this is just set notation. We have the elements that are complex numbers such that, that's what this colon denotes, such that the magnitude is equal to 1. And that is actually the equation or the relationship that defines the unit circle in the complex plane. And I'll draw a diagram of that in a moment. But first, I want to talk about some properties of this group. We can actually parameterize the circle using an angle. I'm going to call that angle theta. So we can say theta can be used to parameterize the circle. Theta can be used to map that angle, and we can actually map it using the complex exponential function. So I can write e to the I theta over here. And we've used complex exponentials in a lot of videos in the quantum mechanics playlist. So when I was talking about trigonometry and the complex plane, this combination, e to the I theta, kept appearing again and again and again. This can be written as the sum of cosine of theta plus I sine theta. So that's Euler's formula, and it's a very useful formula. And that can actually allow you to write the horizontal and vertical components of all the points on the unit circle. So the unit circle is just all the points that have a magnitude of 1. They are 1 away from the origin. So we're not including points that are inside the circle or outside the circle. We're just on the circle. Now let's have a look at some properties of this mapping. So we're using the complex exponential function to do this mapping. We're taking a real number and we're turning it into this complex number. So one essential property is that if we multiply e to the I theta 1, so this is some angle theta 1, we multiply that by e to the I theta 2, that is equal to e to the I theta 1 plus theta 2. So this is a way of linking addition of real numbers and multiplication of these complex numbers that live on the unit circle in the complex plane. So in group theory, there's a concept of a homomorphism. And a homomorphism is a way of linking one group structure to another group structure. So groups may have similarities in their structure. They may have similar ways of how the elements are related to each other and how you can combine the elements using an operation. And one way to take that group structure and map it over to another group is using a homomorphism. And a homomorphism just takes that information that's encoded in the group and translates it into the language of another group. And a special type of homomorphism is called an isomorphism. That is a homomorphism that is also a bijection. And a bijection has the property that it's injective and surjective. So in other words, you can find a mapping for every element. Every element has a corresponding element. So that is one of the properties that we're going to be looking at later in this video. But I want to write down another property that actually follows from this property. And that is, if we take the same number, e to the I theta, and we multiply it n times, right? We exponentiate it, right? This repeated multiplication. That is actually the same as e to the I n times theta. So inside over here, we have repeated addition. We are adding theta to itself n times. And over here, we're multiplying this complex number. So this is how this function, this complex exponential, translates multiplication into addition. We are actually mapping an additive group, so this is real numbers under addition, we're mapping that to a multiplicative group. Here, the operation is addition, and here, the operation is multiplication. And I'm not explicitly writing a multiplication sign. I could actually put times over here, and that would make it more explicit. But I'm implicitly saying that I'm multiplying these guys together. And I'm explicitly saying that addition is occurring over here. So this is the addition of real numbers. And the addition of real numbers, that is an Abelian group. And it satisfies all of those axioms of groups that we've been talking about in previous videos. We have closure. The addition of real numbers is closed. We have the associative property. We have the existence of an identity element. And the additive identity for these guys is 0. So 0 is the additive identity for the angles. And we also have the existence of inverses. You can just have minus the angle. If you add an angle to the negative version of the angle, that's going to give you back the identity, which is 0. So theta minus theta, that is equal to 0. And we also have commutativity. Addition of real numbers is commutative. And that gives us a commutative group or an Abelian group. And it's also an additive group because the operation is addition. And now what we're going to do is we're going to translate those properties into the complex plane. We're going to have a look at the unit circle in the complex plane. So that's what we're going to do with this definition here. So I'll draw a little diagram. So we're going to have a circle, and all of the elements of the group live on this circle. Now I'm going to draw a set of axes inside here. So you can think of these as the real and imaginary axes, or the x and the y axes. And I'm also going to draw an arbitrary point over here. And I'm going to take a mirror image, I'm going to reflect that point across this horizontal axis, and that's going to take me down here. And I'll draw a line up to here and a line up to here. So over here I've got an angle, which I'm going to denote by theta. And over here I've got an angle that's got the same size. It's the same size as the angle, but I'm going to call that minus theta. So this I'm defining to be the positive direction. We're going up this way, and down is the negative direction. Now let's have a look at some special points. These 4 points over here are very special points. I'm actually going to take those 4 points, I'm going to turn that into another group. So those are very special points, and we'll look at that in a second. But first, let's label these points. So this point I'm going to label as 1. This is the multiplicative identity. And it actually corresponds to the additive identity. If we set theta equal to 0, e to the I0, that's going to give us e to the 0, which is 1. What about on this side? On this side, we're looking at the negative axis. So this is the negative number, so the negative side of the horizontal axis. This is minus 1. Up here we have I, the imaginary unit, and over here we have minus I. So these are the 4 important points. These are actually the points where the axes intersect the unit circle. So the real axis, or that horizontal axis, only intersects the unit circle at 2 points, at 1 and minus 1. And what about the vertical axis? Well, the imaginary axis, or the vertical axis, intersects this unit circle at I and minus I. So those are very, very special points. What about this point? This is just some arbitrary point. I could have drawn it over here. I could have drawn it at any other arbitrary point. And this point is going to be equivalent to e to the I theta. So here we have e to the I theta. We take that angle as an input. We're parametrizing the circle using that angle, and that's going to give us this complex exponential. And what about this point? Well, this is e to the I minus theta. I'm explicitly putting it inside some brackets, minus theta. So this guy is actually going to be the inverse. The inverse of the angle is minus theta. Theta and minus theta are inverses of each other. They are additive inverses. And multiplicative inverses can be seen over here when we take the complex exponential. So I want you to see this property. If I take, I'll write this over here, if I take e to the I theta, and I multiply that by e to the I theta's multiplicative inverse, I'm using the notation for a multiplicative inverse, what is that going to give me? Well, this, if I bring this minus 1 inside over here, this is going to give me e to the I theta times e to the minus I theta. And e to the minus I theta is equivalent to e to the I all of minus theta. We're just moving that minus sign around. So raising this exponential function to the power of -1 is the same as negating what is inside the exponent. And we're free to move that minus sign wherever we want. We could put that minus sign in front of the theta and put some brackets around, or we can factor that minus sign out. And because of this property, this is how we combine two guys together in this group. This property is going to tell us that what we have is e to the I theta minus theta. And that's going to give us 0. So this is equal to e to the I times 0. And that's the same as e to the 0, which is the same as 1. So you can see we're mapping the additive identity to the multiplicative identity. That goes back to that idea of a group homomorphism. A homomorphism is that way of translating the structure of one group to another group. So inside this exponent, we have an additive group of real numbers. And then we're translating that into a multiplicative group. And then standard notation for the additive identity is 0, and the standard notation for the multiplicative identity is 1. So we can see that multiplying any complex number, so any element of this group can be written in this form, and it has an inverse. It has a multiplicative inverse. And all we have to do to find that inverse is just put a minus sign over here. And then when we use this exponential law, and we combine these guys together, theta minus theta gives 0, and we can just simplify that to e to the 0, and that is equal to 1. So this is the property where we have the existence of a unique inverse for all of the elements. All the elements have an inverse, and there exists an identity. So we actually have satisfied all of the group properties. So we talked about the group properties for addition of real numbers, and all the group properties actually get translated into this multiplicative group as well. Commutativity works, associativity works. That's because these are complex numbers. This is a subset of the complex plane. So we have to have those properties inherited from the complex numbers. So they're a subset of a bigger set, a bigger group of the multiplicative complex numbers. And the complex numbers under multiplication excludes the origin, because the origin is 0. And 0 has to be excluded from a multiplicative group because it does not have a multiplicative inverse. So we learned that in the axioms for a field in the previous video. So now we've understood the circle group. The circle group has a lot of applications. So especially in quantum mechanics. That's why this is in the quantum mechanics playlist. We're going to be using the properties of this circle group very frequently. Now, what I want to do is I want to examine some smaller finite groups that we can get from this circle group. First, let's consider the simplest possible group. What is the most simple possible group that we can find? It's called the trivial group. It's a group that just contains the identity element. It's not a very interesting group. You can define an operation that takes the identity element and combines it with the identity element, and that spits out the identity element. So that's all the interesting structure in the trivial group. The next most simple group is a group containing two elements. We have an identity element and another element. So let's write down what that group is actually going to look like. We can find that group, and that group has a special property. It's linked to some of the elements over here. So what I'm going to do is I'm going to write down a Cayley table. The Cayley table is a very nice way of visualizing finite abelian groups. And sometimes they can be non-abelian as well. So I'm going to consider the group under multiplication. We're going to have a multiplicative group that just contains two elements, 1 and -1. So this is 1, and then we have -1. And I'm going to draw this multiplication table in this way. I'll draw this just to separate the headers. So 1 times 1 is 1. Over here we have 1 times -1. Over here we have -1 as well. And -1 times -1, that gives us 1. So this is a very simple Cayley table. There's only two elements in this group. And there are four possibilities of combining these guys together. So on the diagonal, we have the identity element 1. -1 is its own inverse, because when you multiply -1 by itself, you get 1. You can think of this visually in the complex plane, in this circle group representation over here. If you multiply by -1, that reflects you over to here. And then if you multiply by -1 again, you get back to where you started. So -1 is the same as reflecting over 180 degrees, or going pi radians around. So you're hopping over to the opposite side of the circle. Now, this group has some very interesting properties. It is actually linked to another group. And that other group is linked to modular arithmetic. So if we consider the integers mod 2, so this is notation for integers mod 2, under addition, we can write a similar Cayley table. So consider the operation of addition, then we have 0 and 1. Over here we have 0 and 1. And then I'll draw these guys over here. These guys are just to separate the headers. If we add 0 and 0, that's 0. We add 0 to 1, we get 1, and the order doesn't matter. And finally, 1 plus 1 is equal to 2, but because we're dealing with modular arithmetic over here, 2 is the same as 0, right? Because if you divide 2 by 2, that gives you a remainder of 0. Have a look at these two Cayley tables. So here we have a multiplicative group with 2 elements, and here we have an additive group with 2 elements. Both of these groups are Abelian groups, or commutative groups, because if you reflect over the diagonal, you have the identical elements. So reflecting over the diagonal gives you exactly the same thing. But we can actually do a mapping. We can take this multiplication over here, and we can turn multiplication into addition. And we can take this 1 over here, and we can take that 1 and turn that into a 0. So if we turn that 1 into 0, then we're going to take this identity and map it to this identity. Now, let's take this minus 1 and take that and turn that into 1. Then we essentially have the same group. So what I've done over here is I found a one-to-one correspondence for all of these guys, all the elements. And there's only 2 elements to worry about. So it's a very simple way of translating from this group to this group. So remember how I mentioned a homomorphism. It's a way of linking the properties of one group to another. There's another special type of homomorphism, which is called an isomorphism. And an isomorphism is a homomorphism, which is also a bijection. And this over here, this is a bijection. I have found something that is both injective and surjective. I have mapped this identity element to the other identity element. And I've mapped this other element to the only other element that exists in the group. So 1 is the standard notation for the multiplicative identity, and 0 is the standard notation for the additive identity. So these are identical groups. The only thing that separates these groups is the labeling. And if we just relabel, we have the same group. So these groups are isomorphic to each other. That is this property. They're isomorphic. They're essentially the identical group. Okay, now let's have a look at some slightly more complicated groups. I'm going to have a look at some more modular arithmetic. So I'll write this in a different color over here. Let's have a look at the integers mod. So we looked at integers mod 2. Let's have a look at integers mod 3 under addition. So under addition, I'm going to have, let's do a plus sign over here. We're going to have 0, 1, and 2. So there's only 3 elements in the integers mod 3. So I'm also going to have 0, 1, and 2 over here. And these are my headers. And this is the standard way to write a Cayley table. Now, this first row is going to be identical to the header because we're just adding 0. And that's the same for this column. We're going to have 1 and 2 over here. Now, let's have a look at what happens over here. We have 1 plus 1, that's 2. Then we have 2 plus 1, and 1 plus 2, that's these guys over here. They're going to be equal to each other. But 1 plus 2 is equal to 3. 3 is the same as 0 because we're working in mod 3. If you take 3 and you divide it by 3, you get a remainder of 0. So that's why this is 0. What about this guy over here? We have 2 plus 2, that is 4. 4 is 3 plus 1. We have a remainder of 1. So I'll write 1 over here. This is the Cayley table for the integers mod 3. So this is a group of order 3. That is sometimes the terminology that is used. This is a group of order 2, and this is a group of order 3. There are 3 elements in this group. So 0 is the identity element for addition, and 1 and 2 are the remaining 2 elements. And they are actually inverses of each other. 1 is the inverse of 2. You can see that in this Cayley table, if we have 1 and 2, they give 0, and 2 and 1, they also give 0. If we reflect across the diagonal, we get exactly the same thing. And one thing that you may notice in all of these Cayley tables is that every row and every column has all of the elements appearing only once. There are no duplicate elements. So that is a very essential property. There's no duplicate elements in any of the rows or columns. So Now let's expand and go one higher. Let's go to the integers mod 4. And I'm doing this for a very important reason. I'll do this in a different color because we're going to find an isomorphic group to the integers mod 4. So I'll do this down here. We have the integers, this fancy z, mod 4. So again, we're doing modular arithmetic, and we're using the operation of addition. All of these guys are additive groups. So being very clear, I'm putting a plus sign when it's an additive group and a multiplication sign when it's a multiplicative group. So this Cayley table is going to have 16 elements in it. So we're going to have 16 possibilities because there's 4 elements. So we're going to have addition, we're going to have 0, 1, 2, and 3. So we don't go up to 4 because 4 is the same as 0. And then we have 0, 1, 2, and 3. I'll put a line over here just so we separate the headers out. Now, if you look back over here, we had the identity appearing here, here, and here. In every row and in every column, we had the identity appearing once. And then the other 2 elements appeared in some interesting patterns over here. Now let's have a look at what happens over here. If we add 0 to all of these guys, we're going to have 0, 1, 2, and 3. So it's the same as the header. And we're also going to have that property over here. We're going to have 0, 1, 2, and 3. Now, what happens when we add 1 to all of these elements? Well, here we're going to have 0 plus 1. That's going to give us 1. 1 plus 1, that's 2. Then we're going to have 3. But then 3 plus 1 is 4. And 4 is the same as 0 when we're dealing with mod 4. Now, let's have a look down here. What's going to happen when we have 1 plus 2? Well, that's the same as this. We have 3. And then we have 1 plus 3, which is 4. And that's 0 mod 4. And now this final little box in the bottom right, 2 plus 2 is 4. That's 0 as well. 2 plus 3 is 5. 5 is 1 more than 4. So we're going to have 1 here. And because it's symmetric about the diagonal, we have an abelian group. So that's 1 as well. 2 plus 3 and 3 plus 2 are both equal to 5. And 5, if you divide by 4, gives you a remainder of 1. And finally, 3 plus 3 is 6. And 6 is 2 more than 4. So that gives us 2 over here. And you'll notice that in every row and in every column, we get all the elements appearing only once. There are no duplicate elements. And have a look at the pattern. We have 3s on this off diagonal over here. We have 1, 1 over here, and 1, 1 and over here. And we have 2s appearing in this pattern, and 1s are appearing in that pattern that we just described. This same pattern is going to show up in another group. So the reason I've written this down here is because I'm going to write another group that is related to the circle group. So do you remember earlier in the video how I took just 2 elements from the circle group, 1 and minus 1, and I formed this group of order 2, this group that only contains 2 elements. Now let's take a group of order 4. Let's take 4 elements, those 4 elements that intersect the axes, 1, I, minus 1, and minus I. We're actually going to find that that group is isomorphic to this group that I've written in red. So I'll do that up here. So over here we had addition, now we're going to have multiplication. So I'll try and line this up. We have multiplication, and what are the elements in this group? Well, there's 4 of them. We have 1, then we have I, and we have minus 1, and then we have minus I. And I'm keeping them in this order because this is the order they appear when we go around the circle. First we see 1, then we see I, then minus 1, minus I, and then finally 1. So minus 1 corresponds to half a rotation around the circle, which is pi radians, or 180 degrees. And multiplying by I, that corresponds to a quarter cycle rotation. So a quarter way around the circle. And minus I is a quarter way around the circle in the opposite direction. So they cancel each other out. So a quarter way around the circle, that's pi on 2 radians, or 90 degrees. If we have I, if we multiply 1 by I, that's going to get us to I. And then if we multiply back, that's going to give us minus. So if we go back, that's the same as multiplying by minus I. That's why these guys are actually inverses of each other. And one thing you might have noticed when I was writing this out is that the complex conjugate actually gives you the inverse. That's why minus 1 is its own inverse. And 1 is also its own inverse, but 1 is very special because it's the identity. If you're a real number, then you're equal to your own complex conjugate. So taking the complex conjugate of a real number doesn't change the real number. That's the reason -1 has that property where it's equal to its own inverse, which is what we saw in this Cayley table. But I is not equal to its own inverse. I has an inverse that's equal to its negative. So negating I gives you that inverse. And I've used that property in a lot of the quantum mechanics videos. When I take the reciprocal of I, that's the same as negating I. Now, let's finish this Cayley table over here. So I'm specifically choosing this order. Now, I have 1, I, then I have -1, and finally minus I. And I'm going to draw this over here just to separate the headers from all of these 16 values that we're going to get. So there's 4 elements, 4 times 4 combinations, which is 16 combinations. They're not all unique. Right? Some of them are going to give the same answer. A lot of them are going to give the same answer. So the first column over here is just multiplication by 1. So the first row and the first column are going to look identical to the headers. So we have 1, I, -1, minus I, and then in this column over here, we're going to have 1, I, -1, and then finally minus I. This property that the headers look exactly the same as the first row in the first column, that only holds if you put the identity element first. And that is the convention that I'm using. That's the easiest convention because you can see you start with the identity element. And in all this modular arithmetic, the identity element is 0 because we're dealing with the operation of addition. But now we're doing multiplication, so the identity element is 1. So I've kept this order, which is consistent with the order of going around the circle in this manner, in this direction. Now let's have a look at some of the other elements. We have to fill out these 9 remaining answers to the multiplication. So I times I is the same as I squared. Let's have a look at this diagram. If I go I, that's a quarter rotation. So I start from the identity, multiply by I, 1/4 rotation, and I go 1 more I. That takes me to -1. So this is -1. Then what happens if I take I and I multiply by -1? So I is up here, and -1 is the same as going a half rotation around, so pi radians around the circle. And that's going to flip me over down here. That's going to take me to -I. So if I go I to -I, that's the same as multiplying by -1. So that is going to give me -I over here. -1 times I, that's -I. And if I reflect over, I'm going to get an abelian group. I times -1 is the same as -1 times I. So I'm also going to get -I over here. And if I go back over here, if I do the opposite, if I take -1 and then I multiply by I, so I'm going -1, that takes me halfway around the circle, and then another quarter way around the circle. So I'm at -I. So I've gone here and then here. Whereas if I swap the order around and I multiply by I first, I go up to I, and then I go down to -I. So this is commutativity. It's an abelian group. So I have those guys. Now, let's fill in this last one here. I times -I. Well, I've already mentioned that I and -I are multiplicative inverses. If you multiply a number by its multiplicative inverse, you're going to get the multiplicative identity, which is 1. So now we have 1 over here. And it's the same over here. We have 1. So anytime you see a 1 or the identity element appearing in the Cayley table, that actually allows you to match up the elements with their inverses. So -1 is actually its own inverse. So we're going to have a 1 appearing over here. So I and -I are inverses because 1s appear over here, and -1 is its own inverse. That is what we saw in this Cayley table, which is a group of order 2. Now, let's have a look at this final little 3 elements here. -1 times -I, well, the minus signs are going to cancel. We're going to get +I. And that's the same over here. Let's have a look at the diagram. What does that look like in the diagram? If we multiply by -I, that's going to, so we start at the identity, we go -I, that takes us down here. And then we're multiplying, so we have -I, we're combining it with -1. So we go -I, and then we hop up over here. We go a half rotation upwards. And it doesn't matter if we go this way or this way, we're going to the opposite side of the circle. That takes us to I. What if we multiply by -1 first, and then we multiply by -I? So we have -1, that takes us to this side, and then we go by -I, that's going to backtrack. We're going to go back to I. So this, and then this. That is what this is describing over here. So multiplication of -I and -1 gives us +I. And then finally, what's -I times -I? Well, if we go -I times -I, we're going 2 quarter rotations, and that's the same as a half rotation. A half rotation is -1. So we have -1 over here. And another pattern you might notice is that we have 1i minus 1 minus I appearing over here. And then all we're doing is we're just shifting them over to the left. And the one that comes out on the left appears on the right. So you can see I gets mapped over here to I, -1 goes to -1, minus I goes to minus I, and this 1 comes up from the other side. And then we keep doing that to get the next row. This -1 goes down, minus I comes down, 1 comes down, and this I comes from the beginning. And finally, we do that one more time, minus I comes down, 1, I, and this -1 was at the start over here. This pattern is exactly the same as what we see in this Cayley table. Have a look at the elements. Which elements can you map to find a bijection? To find a bijection, what we need to do is we need to, again, take multiplication, take the operation of multiplication, and turn that into addition. Right? Then, what do we need to do? We need to take the identity element for multiplication, that's 1, and we have to map that to the identity element for addition, that's 0. So 1 goes to 0. What's the next element that appears over here? We have I. So I'll write down all the elements. We have I, -1, and minus I. Those are the 4 elements. So let's see what we have to map them to. Where is I going to get mapped to? If we take I over here, what does that correspond to in this additive group? Well, here we have I and I appearing in this diagonal, and then we have another pair of I's appearing in this diagonal. That is exactly what we see for the 1s. The 1s appear over here. We have 2 1s on a diagonal, and then another diagonal of 1s over here. So I is going to get mapped to 1. What about -1? -1, there's 3 -1s on this diagonal over here, and then a -1 by itself in the bottom right. Here we have a 2 by itself in the bottom right, and then we have 3 2s on this diagonal. So then we're going to have to map -1 to 2. And then finally, the only remaining one is 3, and 3 appears on the diagonal, on the off diagonal. This is the off diagonal. This is the leading diagonal, and this is the off diagonal. So we have 4 3s. We have all of these 3s here. And those are actually the same as this minus I. We only have minus I appearing on this off diagonal. So we can finally finish this mapping. If we take 1, I, -1, and minus I, and map them to 0, 1, 2, and 3 respectively, and we take the operation of addition, and we turn that into, we take multiplication, we turn that into addition, we will get this bijection. So I'll put this in a box. We have found a bijection. So this is a homomorphism. It's a way of linking the properties and the structure of this group to this group. And it's also a bijection. It's both injective and surjective. Every element has a buddy. Every single element has a unique buddy. So it's not just that one element gets mapped to multiple elements. It's every element gets mapped to a unique element. So that is the property of a bijection. So if this is satisfied, we can say that these groups are isomorphic to each other. They're essentially the same group, just relabeled. Another interesting point that I want to stress on is this parametrization of theta. You can choose to restrict theta. You can choose to restrict theta to only give values between 0 and 2 pi radians. Or you could also find a restriction where you go from -pi to +pi. That's another restriction. What you're doing is you're just slicing the circle up and you're turning it into a line. So you take the circle and you turn it into a line. And that is how you would parametrize theta if you only want to have one unique value of the angle associated with each complex number. If you do not put that restriction on theta, if theta is allowed to be any real number under addition, that's the group that we have here, then you're going to have multiple angles, in fact, an infinite number of angles for each complex number. Because going around one full revolution gets you back to the same point. That is an unavoidable property of being on a circle. One final thing I want to say is the property of closure. If you're on this circle, if you're parameterized as an angle, so let's say you have an angle on the circle, and you add to that another angle on the circle, you are only going to get another angle that lies on the circle. So combining 2 elements of this circle group is going to give you another element on the circle group. You cannot escape the circle. You are stuck on the circle. That is the property of closure. So you can't go inside the circle or outside the circle. The universe for this group is only the circle. So what are the types of groups we've looked at in this video? We looked at an infinite group. We looked at an infinite Abelian group. That is this circle group. Then we took a subset of that, which is only 2 elements. We took 1 and -1, and we turned that into a group. And it turns out this is isomorphic to the integers mod 2. This is a very famous group. This is used in binary, right? So this is linked to binary numbers, which is one of the mathematical building blocks of how computers work. So this is an essential group. It's the group of order 2. Then we also looked at the group of order 3, which is isomorphic to the integers mod 3 under addition. This is an additive group. It's also a commutative group. And then we went one more above that, and we looked at the integers mod 4 under addition. And we found that the integers mod 4 under addition is an Abelian group, which is isomorphic to this multiplicative group. And this multiplicative group is a subset of the circle group. We just take these intersection points, these 4 important intersection points, and we combine them together, and we turn that into this group. And these Cayley tables are a really fantastic way of visualizing what is going on with this operation. You get to see every possible combination of 2 elements. And that is an essential tool in finding bijections between the groups. I specifically chose the ordering here and the ordering here so that we could clearly see the same patterns emerging when we find our bijection. So this in this box, we have a bijection over here, and in this box, we also have a bijection. So just remember that a homomorphism doesn't necessarily have to be a bijection. It doesn't have to be injective. It doesn't have to be surjective. A homomorphism just has to link the properties and preserve the structure of one group when you translate between one group to another group. So it is a way of translating the language of one group to the language of another group. And it's usually another operation. It doesn't have to be the same operation between those groups. And we found in the translations that we did in this video, we went from multiplication to addition and backwards. You can go back from addition to multiplication. Now that is the central property of being a bijection. You can go backwards. There's an inverse version of this. All you have to do is turn the arrows backwards. All of these elements have a unique partner in the other group. So you can actually relabel this to any kind of combination. You can put diamonds and stars and whatever symbols you want. You can use letters. But what we're doing in this video is we're specifically linking it to modular arithmetic. So here we have modular arithmetic, which is giving us additive groups, and then we have a multiplicative group. We're going to keep talking about this unit circle in the complex plane, because in quantum mechanics, this has very important significance. A lot of the eigenvalues of unitary operators can be written in this form. So this is a very essential group. And also, if you zoom in to the circle group, if you zoom in very, very closely, it has the same local properties as just a normal Euclidean space, as a one-dimensional Euclidean space. This looks like the real number line. But if you go and you look at the global properties, the overall properties of the entire space of this one-dimensional sphere, this circle, you'll find that you come back to yourself. So the topology is unavoidably different from that of the real axis. So if you just have the real axis, you can keep going in this direction or you keep going in that direction, and you're never going to come back to where you were before. But in the circle, if you keep going around, you're going to come back. So if you go 2 pi radians, if we're parametrizing by an angle, you will always come back to the same point. That is why this over here is not always going to be a bijection. It's not going to be a bijection because there's multiple ways, in fact, an infinite number of ways of writing each complex number. All you have to do is add an integer multiple of 2 pi radians to your angle. And that's going to give you that property of uniqueness is going to be lost. So let's conclude for this video. What have we talked about? We've talked about some interesting groups. We talked about the circle group, and we used the concept of a Cayley table to find bijections and isomorphisms. We showed some interesting groups are isomorphic to each other. That means they have exactly the same structure if we relabel all the elements. You can find other videos in the quantum mechanics playlist if you click over here.